All right, so yesterday we finished up talking about resonance a little bit, and we said that Lewis dot structures don't always tell a complete picture of what's occurring in a molecule. And the example I gave was this formate ion, where we said if you draw the Lewis structure on the left, we would expect that CO double bond to be the shorter bond and the CO single bond to be longer. The reality is each of those CO bonds is the same length, and we're distributing that negative charge across both oxygen atoms. And we said that there's an example we can look at with this allyl cation, and it makes a lot more sense when we think about this in terms of orbitals. And we identified each of those carbons as sp2 hybridized, which means we've got a leftover p orbital sticking up and down off of each of them. That pi bond can delocalize across all three of those p orbitals. So each cc bond is the same length, just like we saw with that formate anion. That means the positive charge is being shared across the carbon on the far left and the far right. Let's take a look at a slightly different example, though. This example is a little bit trickier. So in this example, we still have three carbons. I'll have a hydrogen coming off here, here, and all of these. However, the carbon on the far right has a lone pair, which would give it what charge? Negative, right? Carbon has a valence of 4, but this has 5 electrons around it, so we'll designate that carbon with the negative charge. Let's do the same thing that we did with the allyl cation and identify the hybridization for all of these. So the carbon on the far left, is it going to be sp, sp2, or sp3? sp2. So we'll have a leftover p orbital. What about the middle one? sp2. What about the one on the right? Ah. So people are saying sp3? I'll put a question mark. Let's take a look at this using the molecular orbital picture. So I'll draw it down here. I'll have a carbon, carbon, carbon. And off of these two carbons over here, we know we've got p orbitals sticking straight up and down. So we're forming some sort of pi bond. And then the carbon on the far right has a negative charge. We know that molecules typically aren't happy with the negative charge. That negative charge doesn't want to be localized on one specific atom. It would prefer to share that burden with other atoms, right? So what ends up happening is this lone pair will actually go into a p orbital. This way, just like we saw with the cation example, it can delocalize across multiple atoms.
Should the double bond still be drawn?
I'm trying to show that pi bond through the orbitals. So yes, you're correct. This is a double bond because we've got a sigma and a pi.
But it's implied because of the pi.
Yeah, it's implied because of the pi. And we'll do a little negative charge right there and there. So by putting that lone pair in the p orbital, we're able to move it across that carbon on the far right and the far left. Just like we saw, we can move that positive charge in a similar manner. We need to include brackets with this to show that these are resonance structures. But now the question is, going back to this part, is that carbon sp3 hybridized? No, it has to be sp2 hybridized in order for a p orbital to be there, right? Another way of thinking about it is, in this resonance structure, we've got a pi bond there, right? So the resonance structure on the far right, we're showing it as sp2. So the reality is, the Lewis dot structure doesn't fully explain the hybridization here. All three of these will be sp2. So let's make a little note of that up here. So the Vesper theory predicts that far right carbon to be, sp3. But it is actually sp2, so that the negative charge can delocalize. So this is interesting. If we look at this carbon coming off of there, what's the geometry going to be? Ah. Yeah, in this case it'll actually stay trigonal planar, even though Vesper theory would try to tell us that it should be tetrahedral. It's going to adopt that trigonal planar geometry, and it's going to have that extra p orbital so that that negative charge can move around across multiple atoms. So it's a little conceptually challenging. What we're going to do is we're going to take a handful of examples and practice them a bunch today. And then tomorrow we're going to have a full worksheet, and you guys are going to break up into groups and try to solve each of them on your own.
So are we going to learn like some kind of a cue to know when that's the case?
Yeah. We'll practice it so you know, hey, this looks like it should be tetrahedral, but is it? And we'll kind of test ourselves to see if we can spot those situations. Let's go over the basic rules of resonance, though. We've seen some of them already. First rule is you don't talk about resonance. That's a joke. First rule is don't break sigma bonds. If you saw in the previous example, we moved lone pairs around and we moved pi bonds around. You cannot move the electrons in sigma bonds. They're going to be localized in that sigma bond. Number 2 is don't ever exceed an octet of electrons. No Texas carbons. I told you guys that's my ultimate pet peeve, and it's something that students occasionally mess up on with resonance structures. Number 3 is getting back to part 1 where I said only move lone pairs and pi bonds. And then number 4 is we're going to move these electrons using arrows. So we'll use arrows to push electrons. The types of arrows we use are typically single-headed arrows. We don't have a cross on the end like we saw with dipole arrows. It's just your generic arrow. The way the arrow is pointing is your electron destination. And this will be your electron source. We'll be using electron pushing arrows a lot in organic chemistry. Remember that the arrows are always showing the movement of where electrons go, not where protons go. It's easy to flip-flop those. So I've got a few examples that will hopefully clarify the idea of resonance. The first one is from my old advisor, and I really like this example, even though it's cheesy. We've got a blue horse, that's one resonance structure, and we've got a red donkey, that's the other resonance structure. We'll bracket these together, And then oftentimes what I do is I like to draw the hybrid structure. So it's not that resonance structures are constantly flipping back and forth. It's that they're more an average or a hybrid of the two. So what would the hybrid be if we mixed a blue horse and a red donkey?
Purple.
A purple mule, exactly. So this molecule isn't adequately described by either resonance structure, but we could say the hybrid structure is more like a purple mule. People get that concept mixed up a lot. They think it's constantly flipping from a red or a blue horse to a red donkey, black to a blue horse. No, it's just a purple mule. We can't draw a purple mule, so we draw it using our resonance structures. So let's draw our cation example. And we'll do the same thing where we draw our hybrid structure. Okay, so we know that positive charge on the far right carbon is going to be delocalized over to the carbon on the far left. So should I draw my electron pushing arrow like that? No, we can't move positive charges. We can only move electrons, right? We said we can only move lone pairs or pi electrons. In this case, we don't have any lone pairs. We only have pi electrons. So what we can do is we can take this pi bond and we can move it over here. Let me clean that up a bit. So we'll show that with an arrow that looks like that. Now the carbon-carbon bond on the left is a single bond. Carbon-carbon bond on the right is a double bond. We haven't moved any hydrogens at all, so those are still in there. But now that positive charge is located over on this carbon. And again, we need to remember to connect these with the double-headed arrow and bracket them. And then let's draw the hybrid purple mule structure on the right. So we know the sigma bonds were untouched during this whole process, so I'll just draw all our sigma bonds out, and then we'll draw our pi bonds next. So is the carbon-carbon bond a single bond, a double bond, or in between? In between. So oftentimes to show these hybrid structures, like you guys saw previously, I just show that as a dash, meaning that pi bond is delocalized across 3 atoms. That means over here, this carbon's got a delta positive, this carbon's got a delta positive. Neither of them is forced to carry that burden of a full positive charge. It's distributing it evenly. So technically, we can even think of each carbon on the left and right as carrying a positive 1/2 charge, and they're sharing that equally. Let's do the same thing with our anion.
Why didn't the right resonance structure have the electron pushing on it? Or do you just do that once?
So another way of thinking about it is we can show it going from the right resonance structure back to the left by having another arrow. And you can show it either way. That's a good question.
You only have to do it once then?
Typically, I want to see your work going from left to right. So you don't have to show arrows going left to right and right to left unless I specifically indicate that. That's a good question. All right, let's do our anion. All right, this time we know that carbon on the far right has a negative charge, but it's going to share that negative charge with the carbon on the far left. So now the question becomes, can I take this electron and move it directly over there?
No.
Why not?
Wouldn't you just take the lone pair, make a double bond there, take that double bond and make it into a lone pair on that carbon?
Okay, let's just play devil's advocate though for a second. And let's say I do that. Let's say I move this lone pair over here. Does that look okay? Violates the octet rule. We can't do that. That would be an example of a Texas carbon. So what we're going to do is just move it to the adjacent bond. So this lone pair will now become a pi bond. And then this pi bond will become a lone pair. So we actually have to use 2 electron pushing arrows to show that movement of the negative charge from that far right carbon to the far left carbon. So now we've got our pi bond. Our lone pair is now on that carbon. That lone pair used to be in that pi bond. And we should always draw our formal charges. Same thing, we can draw our hybrid structure on the far right. We know this pi bond is going to be shared across all 3 carbons, so I'll show that with the dashed line. But now each carbon's sharing that negative charge, and we're not forcing it on any particular atom. Does that make sense? All right, let's do one that's a little bit different than what we've seen. I'll quiz your Gen Chem knowledge here. Does anybody remember what this anion is called?
Ozone if there's no carbon.
Yeah, so O3 would be ozone. Carbonate, exactly. So this is a carbonate anion. Let's see if we can draw some resonance structures for this. And I'll start by just closing this off with a bracket. We know that we can move lone pairs and pi bonds. Specifically, resonance structures try to delocalize charge usually. So what we can do is we can take one of these lone pairs, and where can I move it?
Bond. To the single bond.
Yeah, to the single bond, so this lone pair will become a pi bond. If we do that, though, that carbon has 5 bonds to it. That's not allowed, so we'll have to move some electrons to resolve that. What can we do? Break the double bond, right? Kind of like we saw with our anion above. If we move a lone pair and form a new pi bond, we have to break a pi bond that was attached to that atom. So let's draw our new structure. Now we've got a double bonded oxygen here. Single bond here. Top oxygen has 3 lone pairs, giving it a negative charge. And this oxygen on the far right only has 2 lone pairs, so now it's neutral. All right, are there any more resonance structures we can draw? Yeah, we can keep on pushing this. So let's move this one down here. Oh, sorry, wrong one. Let's move this one over here, and then that one up here. So now this oxygen's negative, that one's negative, and this one's neutral. Are there any more? Yeah, I mean, hypothetically, we could pull this electron up and not violate any octet rules. However, that would give 3 negative charges and 1 positive charge. That's not going to be a major contributor, and we'll talk about which contributors are major and minor in a second. So these would be examples of the 3 major contributors for carbonate. So now what I want you guys to do is to try to figure out what the resonance hybrid would look like. And we'll draw that over to the right. Remember, with the hybrid, I always include all of my sigma bonds, and then I figure out where the pi bonds are delocalizing. Let me zoom out a little. There we go. So where should we include dashes?
Around the entire perimeter.
Yeah, across every bond. If we look, for example, at this bond, it's a single bond here, but a double bond here. That means it has some double bond-like character, right? So we want to show that by having a dash. In reality, this is probably more like a bond order of 1.33, right? So it's not quite a bond and a half, but it's not still a single bond. It has some double bond-like character. Same thing with this top one. If we look at this top carbon-oxygen bond, it's a double bond here, single bond here, single bond here. So again, it's probably a bond order of 1.33, and then the same's true of this last one. All right, and we know that negative charge is delocalized across all three oxygens. So we can say, all right, these oxygens always have at least two lone pairs coming off of them. However, there's going to be high electron density coming off of each of these oxygens, because in at least some of the resonance structures, they're carrying a negative charge. If we think about the negative charge coming off of them, if we had to assign a numerical value to it, would it be -1, -1/2? What would the fraction be? Yeah, -2/3. So each oxygen is carrying a -2/3 charge if you wanted to assign a numerical value to it. Does that make sense? A lot of people say, well, if we were looking at carbonate, isn't that the same structure just spinning around? Not quite. We still need to push electrons even though it looks like the exact same structure that's spinning around. That's to show that it's not one molecule that's spinning, that those pi bonds don't belong on any particular set of atoms, that they're delocalized. All right, the next part is identifying electrons that can delocalize. So I'm going to draw an example, and we're going to compare it to an analog that looks pretty similar. I'm not going to use bond line structure for now, just so we can keep track of everything. But let's do a little pop quiz. What's this functional group?
Amine, because there's no oxygen double bond to a carbon.
Amine. All right. How about somebody in the back? What's this functional group? An alkene. All right. So we're passing our pop quiz. That's always good. And let's try to determine if there's any resonance structures for this. What do you guys think? Okay. Let's say I try to move this pi bond over here. Is that allowed?
Breaks octet.
Yeah, then that nitrogen, if it had a double bond to that carbon, would have too many electrons. So we can't move the pi bond that direction. Okay, that leaves us with the lone pair. Can we move the lone pair over here?
No, because it breaks the carbons.
Yeah, the carbon would violate its octet, but is there any way to solve that?
What if you
You move the hydrogen.
move the pi bond to the right and then, oh wait, no, that was
No, I think you're totally on the right track. So you said move the pi bond to the right.
yeah.
So if we do that, that central carbon doesn't violate the octet rule, and the carbon on the far right will now have a lone pair. So let's draw that out. So this carbon has a lone pair. Now we've got to start assigning formal charges. The carbon with the lone pair, what charge would it have? Negative. So we'll just do a negative symbol. What about the nitrogen? Positive. Okay, that means that this set of electrons in that lone pair orbital can delocalize, which means nitrogen has what hybridization? sp2, right? Because if we look at it over here, this nitrogen's sp2 hybridized. So this nitrogen must be sp2 in order for delocalization to occur. And last but not least, we'll bracket these in together. Let's take a look at an analog that looks pretty similar. Same backbone. However, we've got 2 hydrogens coming off here, 2 hydrogens coming off here. Got our lone pair. Now the question I have for you guys is, can we delocalize that lone pair on nitrogen? Not everybody all at once. Well, let's try. Just for sake of argument, I'm going to move this lone pair down here, and let's draw what we get out. Is that okay? What's wrong with this?
Hydrogen would never come in.
Well, Texas carbon, yeah. If we look at this, this is a big fat frowny face. We can't draw Texas carbons. That's not allowed. We're violating the octet rule. So this molecule will not exist. That means there are no resonance structures for this compound. And if we think about this nitrogen, what hybridization will that nitrogen be if there's no delocalization of that lone pair? sp3, exactly. So this one will be sp3 since delocalization cannot occur. All right, so anytime you're trying to determine the hybridization of an atom from here on out, check to see if there's a resonance structure that you can draw. If there's a resonance structure, that could change the hybridization of that atom. If there are no resonance structures, stick with your gut and go with your original Vesper theory prediction. All right, now let's take, yep.
So there is only one lone pair for pi bond molecule out here in the structure.
Yeah, so if you only have a lone pair and there are no pi bonds, there's not going to be any good way to move electrons around in most cases. However, what if, just for the sake of argument, this carbon were positive? Then could we move that lone pair? Yeah, then we wouldn't violate the octet rule. So there are some exceptions to that. The main thing is always double check that you're not drawing a Texas carbon or that you're not violating an octet rule.
So basically you need pi bonds to move electrons around?
You need pi bonds or lone pairs. You'll see examples of both.
I have a question on the previous example.
Mm-hmm.
If you were drawing is there a way to draw the structure like the purple mule structure?
For the top one?
Yeah. Would
Yep.
it just be the 2 dotted lines and then a delta positive and delta negative on each one?
Yeah, let's draw that real quick. So we'll do nitrogen. Whoop. This is actually a good segue into our next topic. It's almost like I planted the question. So this would be a dash going across these atoms, right? And if we think about the nitrogen's got a partial positive on it because in one of the resonance structures it has a positive charge. And the carbon will have a delta negative since in one of the structures it has a negative charge. But let's just stop and think about this. We've got two resonance structures drawn. Do you think they're both equal contributors, or do you think one's more important than the other?
So left one.
Do you guys think the left one's more important or the right one? Or do you think they're both equally important?
Left one, because the right one's not as stable by having two formal charges that are unnecessary.
Yeah, oftentimes when we draw molecules, it looks funny to have a bunch of charges on there if we can draw a Lewis structure that doesn't have charges, right? So the one on the left looks a lot more appropriate just because it doesn't have any charge, right? So that gets to the next point. Not all resonance structures are of equal importance. There are major contributors and minor contributors. The one on the left, or at least the top left, is going to be your major contributor, and the one on the right is going to be a very minor contributor. But let's make some rules for determining which ones are major and minor. So rules for determining the importance of resonance structures. Oh no, I'm running out of room. Okay. Number one rule, most important rule, is that full octets take priority. And I'll show you an example of what I mean. Let's take the example we looked at last week, carbon monoxide. So CO. We could draw out CO like this. What would the charge be on the carbon? Negative, which means our oxygen is going to be positive. Let's determine if there's a resonance structure for this. What if I take this pi bond, or one of the pi bonds at least, and I move it over to that oxygen? We could try doing that. Turn this into a double bond. Now this oxygen has two lone pairs. This carbon only has one. What's the formal charge on oxygen now?
2 minus.
So it normally has a valence of 6. We've got 1, 2, 3, 4, 5, 6. So it's neutral now. What about carbon? It's neutral. Technically, following our assignment of determining formal charges, carbon and oxygen are neutral for the compound on the right. However, this carbon, let me actually use a different color, doesn't have a full octet. That means if we're looking at this set of resonance structures, the one on the left is actually going to be the major contributor. The one on the right is going to be the minor contributor. This one will be our minor contributor. So this is the first thing to check for. Your major contributor, if there is one that has a full octet, will be assigned as the most important resonance structure. That leads to tiebreaker rules. The next one is if all atoms have an octet, then the structure with minimized charge takes priority. So that's our tiebreaker for number 2. Then we've got another rule. Let's say you've got two structures that both carry charges. How do we assign priority if they both have charges and they both have full octets? Then we need to look at the electronegativity of the atoms carrying the charge. So if comparing two structures with full octets and the same charge, then the one with the negative charge on the more electronegative atom takes priority. Or another way of thinking about this is the positive charge wants to be on the least electronegative atom. Sorry, I know this is a lot of writing. So that's rule number 3. We want to try to put the charge on the atom that's happiest carrying that charge. And then rule number 4 is it's pretty simple. It's avoid drawing a resonant structure with both carbon bearing a formal charge and carbon bearing a negative charge. That just looks kind of funny. A good example of that is once in a while I see people that will try to look at a molecule that has a double bond. And they say, oh, this has a resonance structure. We can move this pi bond up to this carbon. And when we do this, the carbon on the right now has a negative charge in a lone pair, and the carbon on the right now has a positive charge. This is such a minor contributor, we don't even waste time drawing it.
And that would violate wouldn't it violate the first rule? Because there's no octet on.
So the first rule is full octets take priority, and in this case, the carbon on the left, or sorry, this structure on the right, but the carbon on the left right here doesn't have a full octet. But like I was saying, this is such a minor contributor, don't even waste your time drawing it. So we'll do very minor. Don't draw. Save your wrist. All right, so let's take an example of one and we'll try to determine its resonance structures, and then we'll assign priority to each of the resonance structures. So we'll do practice. So this carbon on the far right has a negative charge on it. Try to find at least 2 other resonance structures for this compound. How many of you have at least one resonance structure? Most people? All right, let's take a look at it. Let's do this first. I'm going to take this lone pair. I'm going to push it down and form a pi bond. That carbon would have more than an octet. So what can we do to solve that? Yeah, move the pi bond up to the oxygen, right? We'll turn that pi bond into a lone pair. All right, so now we've got a carbon-carbon double bond, carbon-oxygen single bond. And then, hypothetically, I could say, well, let's move this pi bond up to that hydrogen.
Would that oxygen actually be carrying a partial negative charge just as a full octet?
Yeah, we'll take a look at the hybrid structure and determine which atoms are carrying partial negatives and positives next. But for the middle structure, it has a formal negative charge on it because it's got that lone pair.
But even with the shared electrons, it's 8 exactly.
It's what?
But with the shared electron with carbon, it's just a full octet.
Yeah, let's assess the relative priorities next, though. So if we do this one, we've got that. All right. Rule number 1 says full octets take priority. Which one doesn't have full octets?
Right.
The far right one, right? So we could say this does not have full octets. What's another rule it's breaking that we really don't like? Yeah, positive and negative carbon. We don't really like drawing those next to one another. It looks funny. That means that this one is going to be a very minor contributor. All right, so now we've got to compare the left two, right? Which one do you think is going to be the major contributor between the left two? They both have full octets. Second one. Why do you think the second one is the major contributor, Marcus?
Oxygen will be happier with negative charge.
Oxygen's more electronegative, which means it's going to be happier carrying that negative charge than the carbon. So we can say that this will be major simply because the negative charge is on a more electronegative atom. That means that this is a moderate contributor. All right, we're starting to run out of time, but really quickly we'll draw the hybrid of this. And I'll say, all right, we've got CH3, C, CH2. We've got oxygen with 2 lone pairs. We know that this oxygen is going to carry a pretty substantial portion of that negative charge. This carbon down here will have a little bit of negative charge, so I'll try to draw that smaller. And we'll have some delocalization. Whoa. There we go. And we'll have some delocalization that occurs across both of those bonds. So this would be a good hybrid view.
Which it shows that there's more delocalization on the top one.
Yeah, so which bond do you think is going to be more double bond, like the carbon-oxygen or the carbon-carbon?
Carbon-oxygen.
We said that this is going to be our major structure, which means that carbon-carbon bond is going to have more double bond character than that carbon-oxygen bond. It's not going to be equally distributed necessarily. All right, I think that's where we're going to end off today. Tomorrow we're going to practice a bunch, but try to get started on your problem of the day early, and let me know if you have any questions. And then double check with your classmates too. Don't try to struggle through it alone.